Fly-by-wire was first installed on military airplanes, where there are not the same safety requirements as on civil aircraft, because the crew members have an ejection seat. Later on, when it appeared that the technology was fully reliable, the first civilian transport airplane built with fly-by-wire was the Airbus A320. Now, many recent transport airplanes are equipped with fly-by-wire systems. On fly-by-wire systems, the information of the displacement of the stick or of the control wheel is sent to the computers, which in turn give the orders to deflect the control surfaces, to execute the maneuver requested by the pilot. Let's take an example. The pilot displaces the stick so as to obtain a load factor of 1.5 G. This command is transmitted to the computers. The computers send an order for the deflection of the elevators to reach 1.5 G. This order is a function of speed, Mach, altitude, center of gravity position, etc. The probability of failure of a flight control computer is very low. However, just having a high number of identical computers would not necessarily guarantee an acceptable safety level, as the same bug could affect all computers. For this reason, different types of computers need to be installed, with different hardware and different software. Each computer usually includes 2 computation lanes, with different software. Digital or analog technologies can be used. This is the general principle of dissimilarity implemented by the manufacturers with different architectures. In all failure case combinations that are considered as possible during the lifespan of the world airplane fleet, a sufficient number of flight control surfaces must remain available. For this reason, most of the surfaces need to have 2 servo actuators, driven by several computers. To clarify, let's take the example of the 2 elevators. Just imagine that each of them only had 1 hydraulic actuator, driven by 1 computer. If the hydraulic circuit on one side and the computer on the other side fail, both elevators would be lost, which is obviously unacceptable. In a standard design, usually 2 actuators control each elevator, with different hydraulic circuits, and 2 different computers can drive each actuator. The flight control computers receive a lot of data from various systems and sensors. To get reliable information for critical parameters, a minimum number of sensors is recommended, with a vote between them. In addition, whenever possible, data are compared to other information, such as models, to eliminate a parameter that appears unrealistic. The loss of all generators is obviously a critical situation on a fly-by-wire airplane. In these circumstances, electricity is usually produced by a ram air turbine below the wing or the fuselage, driving a small generator. 2 flight control computers are generally available in this configuration. Even if for some airplanes it is considered that with the dissimilarity and the general architecture a sufficient safety level is ensured, today all fly-by-wire aircraft include a backup mode to cover the failure of all flight control computers. This may be mechanical or possibly electrical. Without any failure and when no protection is active, the aircraft is in normal law. However, normal law can be completely different from one aircraft type to another. The manufacturer chooses the parameters that are controlled by the stick or the control wheel. For pitch in normal law, there are 2 main possibilities when in level flight. Maintain the speed. The aircraft has a positive static stability. When accelerating, it is necessary to push on the stick or on the control wheel, then to trim to stabilize a new speed. The aircraft is flown as if it had mechanical flight controls. This is the solution adopted for the B777 and the B787. Maintain the attitude or the trajectory. With such a law, there is no need to trim when modifying the speed. It is the obvious choice for fighters as it eases fast speed variations. Airbus and Dassault Aviation also made this choice for their fly-by-wire transport aircraft. At a given speed, the control wheel or the stick displacements may command the variation of various parameters such as, for example, load factor or pitch rate, or a mix of both. The knowledge of the center of gravity position is important. At a given speed, the elevator deflection to obtain a load factor is different at forward and aft center of gravity. Not taking into account the CG in the computation leads to an immediate incorrect deflection of the elevators to reach the pilot's target. It is obviously not possible to use the CG directly inserted by the crew because there are sometimes errors and it could have adverse effects on the handling. In flight, for given weight, speed, Mach and angle of attack, the tailplane and the elevator positions are a direct function of the CG position. Therefore, thanks to a simplified aerodynamic model, the knowledge of all these parameters allows the CG to be computed with sufficient precision. Stabilizing the airplane in roll is less critical than in pitch, and a direct law, which means surface deflections proportional to the stick or the control wheel displacements, is the solution sometimes adopted. A roll rate may also be associated to a displacement of the stick or of the wheel. When they are in a neutral position, the bank angle is maintained, if not too high. The most sophisticated lateral flight control law permanently maintains side slip at 0, as on the A380 and A350. On transport aircraft, without yaw damper, there is a Dutch roll oscillation in all configurations, sometimes with very poor natural damping and possibly no damping. On the most recent models, the yaw damper orders are calculated in all computers and are always available. Due to the large wingspan, the behavior of a transport aircraft when starting a turn is more like a glider than a light aircraft. There is a lot of adverse yaw. Therefore, with any aileron deflection, there must also be a rudder deflection to maintain the side slip at 0. This logic, called turn coordination, is installed in the computers. On ground and for takeoff and landing, there are specific control laws, which are often adapted from direct laws. For takeoff, on the most recent models, they are designed to reduce the takeoff distance thanks to a rapid rotation and to minimize the risk of tail strike. Various types of protection may be installed on a fly-by-wire aircraft: pitch, bank, stall, high speed, etc. These may be soft protections that may be overridden or hard protections that cannot be exceeded. It is the choice of the manufacturer. As an example, bank angle may be blocked at values depending on the speed. This is a hard protection. A soft protection could be the installation of audio and visual warnings when the bank angle exceeds certain values.
Banking, 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 banking.
Large airplanes are flexible and there may be comfort issues in turbulence. On fly-by-wire aircraft, the available sensors allow the detection of the various oscillation modes on all axes, and specific control laws damp these motions, at least partially. In case of failure of at least 2 computers or 2 identical sensors, and sometimes more, there may be a reversion to a degraded law. There are many types of degraded flight control laws, depending on the airplane type, on the architecture, and on the failures that cause the degradation. An extreme degree of degradation is direct law, where the surface deflections are proportional to the stick or to the control wheel displacements. Some failure cases lead to a workload increase for the crew. For other failures, the degradation is minor and has no consequence on normal operations. For example, in case of loss of high speed and low speed protections, if the procedures are properly followed, the degradation does not affect the handling and the operations. Fly-by-wire systems have greatly increased the ease of flying and the safety of modern airplanes.